You, I would stay here because then I like to speak with my hands. So, but that's up to you. Good. It should be fine. Yes. Brought me down there and said, "Okay, you be teacher." So good morning. Back to this last two talks, plenary talks. Now we have Andy Hulet from Rice University talking about quantum simulation of many body states of matter with ultracold atoms. Andy, thank you.
Thank you. So I guess Vanderlei's not here, but I'll thank him anyway. And it's kind of it's amazing when I come to San Carlos because of the just the commitment, sheer energy and commitment that goes into not only research but also to education. And it's really inspiring for me to be here and see that. All right, so I'm going to be talking about quantum simulation of many body states of matter with ultracold atoms. This was experimental work that we did at Rice University in Houston, Texas. And about 6 hours ago, my house in Houston was hit by a hurricane. The door blew open, but I think we're okay. And we're glad we're not there. Some other friends had a tree fall on their house, which is never a good thing. The experimental group is in my group at Rice, and we were aided by a number of theoreticians, primarily Jiwen Wan, but also some of his students, Han Pu, who is at Rice, and Terry Giamarchi at Geneva. Okay, so quantum simulation with ultracold atoms works by using the atoms as stand-ins for electrons. So, and the advantage of not using electrons is then the atoms don't experience the same defects and impurities and Coulomb screening and so on that real electronic materials do. So having atoms stand in for the electrons gives you not only the avoidance of some of those unwanted effects, but also allows you to tune interaction strength, tune geometry. You saw in the previous talk today by Hélène that you can make a 2D gas You can also make a 1D and, of course, 3D gas, depending on how the atoms are confined. So I've listed a few of the tunable parameters down here in the lower left. There are things like interactions, hopping. Maybe this will be better. Can you hear me? Okay. Temperature, density, dimensionality, geometry, polarization, spin-orbit interaction, disorder, and time modulation. So all of these things can be put in, and it's limited by, I think, almost your imagination. But all of these effects are not only tunable, but can be, but they are changed in sometimes dramatic ways to make a many-body model behave like a real sample. So one thing I would like to clear up in talking about many-body simulation using ultracold atoms is that we're simulating not the material, for example, a high-temperature superconductor. We're simulating the model. In this case, maybe the Hubbard model, the Fermi-Hubbard model. And so one has to be careful about that. Of course, you make the best model that you can, but the model may not be a good model of a real material. And that's just something to keep in mind. So down here are different states produced by optical lattices. This is a one-dimensional optical lattice that produces an array of two-dimensional pancakes in which you can choose just one if you like in the lens experiment. The 2D case gives rise to an array, a two-dimensional array of one-dimensional tubes. And then finally, a three-dimensional optical lattice just gives you a simple a standard cubic optical lattice. But this is just the start. You know, these are the easy things that you can do. You can do much more interesting. For example, Peter Schaus, who I'm afraid left this morning, but Peter made a triangular lattice in his lab, and triangular lattices are particularly interesting because in the case of fermions, the fermions are inhibited to move, and due to the Pauli principle, which cannot be satisfied in a triangular geometry. So this is what the Feshbach resonance looks like. It doesn't go into the details on how it works, but the basic idea is that you put an atom in a magnetic field, and in this case, this is a Fermi gas, and so I have a spin up and a spin down atom, and they interact in some ways, and the interaction can be tuned by a magnetic field, which produces this Feshbach resonance. And you can see that the measure of interaction strength, which is given by the S-wave scattering length, goes in this geometry, goes from 1500 Gauss, or 1500 Bohr radii to 0 and even negative. And so down in here, in this range, the gas is attractively interacting, whereas over here, where S is positive, the gas is repulsively interacting. All right, so this was one of the first models of many-body physics using ultracold atoms. It was done in Manuel Bloch's laboratory at Mainz at the time. And a Mott insulator is a very famous model of many-body physics in which the atoms are restricted from moving due to the fact that their density in the lattice is 1 per site. And with 1 atom per site in the lattice with repulsive interactions, there's no hopping. So this was the first example, I believe, of a non-trivial many-body state in cold atoms. It was done with bosons, as they say. And what you'd like to do is is fermions because of the connection to electrons. So the hydrogen atom of condensed matter physics, as my advisor Dan Klepner would say, this is a very simple model to write down. This is the so-called Hubbard model, in which you have atoms on lattice sites that can move by tunneling. And when they do, there's some energy that's gained. And if they land on top of each other, then they interact via this repulsive interaction U, which also could be attractive, as I'll mention towards the end of my talk. So we're looking at just single band Hubbard model, and so there's only at most 2 atoms per site that are opposite spins. If they have the same spin, the Pauli principle prohibits them occupying a single band. So this is really a paradigm model of many-body physics, strongly correlated matter, and it's been a proposed model for high-TC superconductivity. So despite the discovery of high-temperature superconductivity being, let's see, about 40 years old, it's a little embarrassing for physics to say that we don't understand how it works. So our goal is to, in these models, is to understand the Hubbard model and therefore, by extension, to try to understand the high-temperature superconductivity. It can't be solved exactly because even though this is simple to write down, it's extremely difficult to solve. And that's because the basis size scales as 2 to the n, where 2 is the spin direction. Okay. So this is the phase diagram of a high-temperature superconductor. This is the doping or the density of atoms on this axis. This is the temperature on this axis. And the first thing you see is if there is no doping, if there's exactly the same number of upspins to downspins with exactly 1 atom per site, then they can undergo a transition to an antiferromagnet at the nail temperature, which is right there. So that's the first non-trivial phase that you encounter. If you're able to get colder, then you can look at D-wave superconductivity in principle. Nobody has, but we're all trying. And one can also look at strange metals in this region above the superconducting dome. So this was our foray into this field. This is work that was done in 2015 in our lab in Houston. The axis here is U over T, so it's the interaction scaled by the tunneling rate. And just like the theory, which has a peak at around U over T of about 12, so does the data. And this was the first measurement of antiferromagnetism in the Hubbard model with cold atoms. And we were able to measure the static structure factor, S of Q, which was just measured by Bragg scattering off of these symmetry planes. Now, so this is the light coming in at the Bragg angle, and it comes out coherently scattered at the Bragg angle. And at any other angle, it would be completely incoherent. Now, in reality, our data doesn't look like that. We don't have perfect antiferromagnetism with order that stretches over many lattice sites. What we do have is antiferromagnetic order, which is over 1 lattice site. And the reason why it's not better is that this is still below or still above the nail transition temperature by a little bit. So we can see that by comparing to quantum Monte Carlo. And I said that quantum Monte Carlo didn't work, and it doesn't when you get too cold, but it does here at the transition temperature. These are different colors that represent different temperatures. 0.5 is the green one, which seems to fit the data the best. And in fact, over that whole range, it fits it perfectly with only one free parameter, which is the temperature, is 200 nanokelvin. So to do this, in order to get the temperatures low enough and the density correct, we resorted to a Bluetooth trap that canceled the attractive contributions from an infrared geometry. And so we could flatten by canceling some of the attraction in the trap. We're able to flatten the density profile. Now, that works pretty well, otherwise we wouldn't have done this. But recently, Jean-Wei Pan in the USTC in Hefei, China, has succeeded in using this kind of geometry and this detection method to get much, much colder. And the way he did it was to make a box-like potential that produces a very uniform density profile. And therefore, when you load the trap, the density is considerably lower. So that's a major, major accomplishment that just happened, just posted to the archive in the last 6 weeks or so. So I just want to acknowledge some of these people before I go on to the next topic. This is Pedro Duarte and Russ Hart, who were the heart of the experiments, and Ernie Yang came a little bit later. So what I want to talk about now is one-dimensional physics. And we decided that since it was so difficult getting low temperatures in the Hubbard model, that this was low-hanging fruit. People hadn't done experiments with 1D geometry. But the idea is that in 3D, electrons are able to move around other electrons. And so doing, the excitations are quasi-particle-like, and they're single particle-like as well, and they're fermionic. And this is something called the Landau Fermi liquid theory. In 1D, as compared to 3D, the atoms can't get around each other. So if there's an excitation here, it will propagate through necessarily through these other atoms. They can't avoid their neighbors. So these are collective excitations. They're sound-like, and they're bosonic, and that description fulfills a model called the Tominaga-Lettinger liquid model that people have been curious about for a number of years. So the particle hole excitations are different in 3D versus 1D. In 3D, we have a continuum of energies for exchanging some momentum q, which is equal to the diameter of the Fermi sphere, and those excitations can have any energy between 0 and the Fermi energy. Now, in 1D, it's completely different because the Fermi surface is not really a surface, there are points. So this is a Fermi point, this is a Fermi point, where Q is equal to 0. And in this case, the Lettinger liquid for low energy excitations has a very limited number of options in scattering and excitation. So the dispersion relation has got this very sharp cusp that is very different than the 3D case. So this really, describes the differences between 1D and 3D. Now, one of the most remarkable phenomena that occur in these one-dimensional systems is something called spin charge separation. So I mentioned that the excitations are sound-like. Well, they can, it turns out, they can be either for spin or the excitations could be for the charge mode, either way, and they have slightly different velocities. And so that means if you excite an excitation, a spin, and a charge excitation, and they start moving down the wire, the charge is going to get ahead of the spin, and eventually they'll be at some distance from one another. And when you think about it, that's pretty weird, because these are, these are electrons. You would expect them to be in violet chunks of matter, but this is a many-body effect, and those perceptions don't apply. So here are the two kinds of excitations. This is a charge mode excitation called the holon, and this is a spin mode excitation. We start with antiferromagnetic order, and then you hit the sample with a laser that either produces charge mode excitations or spin mode excitations. The charge mode, as I mentioned, is velocity exceeds that of the spin mode by this factor of gamma over pi squared. So we set up to measure this quantity, and we looked back at what some other people had done in condensed matter. There were things like power law correlations that were observed in carbon nanotubes. These happen to be nanotubes that were made by Rick Smalley's group at Rice, and they could measure the spin and charge excitations in the nanotubes. So the spin charge separation versus electron density was done by Amir Yacobi and his group a few years ago now. And this is a plot of charge and spin. I don't know why the spin is flat like this. It shouldn't be. It should be changing with interaction strength, and it's not. And the reason why is that in solid state, these quantities are much more complicated than they are with cold atom systems. And it's difficult to make comparisons with theory because of the complexities of things, for example, the Coulomb potential and disorder and defects. So there was a paper many years ago now by Peter Zoller and his group on how to see spin charge separation. And what they proposed was to put in a little dimple in the center of this distribution, and that by exciting that dimple, you excite both spin and charge modes. They're dependent on one another, so in fact, you can't excite one without the other in this method. So we decided to do something a little bit different, which is to use Bragg spectroscopy. So we make an optical lattice, a 2D optical lattice, which results in a bundle of one-dimensional tubes. We fill these tubes up with of order 50 to 100 atoms. And then we can impart excitations by scattering laser beams. This is looks kind of like a Raman transition, but it has both momentum and energy, which are separately tunable. So Chris Vail and his group and Leonardo Filani have done Bragg spectroscopy with fermions. They have not seen the spin charge separation yet. Now, it turns out that one of the advantages of having a system like this using Bragg spectroscopy is that you can measure the charge density wave speed and the spin density wave speed separately. So with a symmetric excitation with the laser beam being tuned long distances, long frequencies relative to these two ground state sublevels, or excite a spin mode, which is an antisymmetric excitation, where the laser beam is detuned halfway between the spin up and the spin down atoms. So this is what Bragg signal looks like. If you look carefully, you can see that this is a nice symmetric distribution of atoms in the trap, and actually released from the trap for a few microseconds. Whereas in here, there's a Bragg pulse present, and it bites a chunk out of this distribution, and that chunk is this red distribution. If you look at the image directly, this is a trough, and this is the excitation. So by doing a one-dimensional line integral, you can map out that Bragg signal as this little dispersion curve. So the dynamical structure factor is related to the amount of momentum that you scatter. So delta P is this momentum, this signal, Bragg signal, and it depends on the difference of these dynamic structure factors, which are dynamic structure factors are the correlations, the Fourier transform of the correlations of either spin or charge. So these are some results from Leonardo Filani's group. They were unable to excite the spin mode for the reasons that I just gave. And we did an experiment later than this one, fairly recently. And we were able to get the charge mode, get the peak velocity of the charge mode as a function of interaction strength. And that's data with no free parameters, with temperature as a free parameter. This was an experiment done by Emmanuel Bloch. It's a two-dimensional geometry where it's called a quantum gas microscope. These atoms are individually addressable, and they hit one, and it produces an excitation that it propagates through the sample, and you can look at the fact that the spin mode travels more slowly than does the charge mode. This is our data. These are the structure factors that come from the scattering of the Bragg pulse. And you can see they agree pretty well. There's some disagreement in here on the spin mode at high interaction strength. But everything else fits pretty well. So the solid lines that are shown here, either for the charge or for the spin, are from the beta ansatz assumption, and the two free parameters is the overall scale and the temperature. So these observed discrepancies, primarily this one, but also in here, are due to nonlinearities. And with nonlinearities, the linear liquid theory is no longer exactly solvable as it would be in a precisely linear geometry. So this is the spin charge separation, which shows that the two speeds are the same at zero interaction here. And as you increase the interaction, the spin density wave decreases in speed while the charge increases. And the dashed lines are the theory. So this is, I think, the first really theoretically accurate comparison to data and theory. So here are some of the nonlinearities that one has to take account of. The band curvature, which is dominant in the case of the charge mode, but backscattering, which is a significant correction only applies to spin modes. And this was really an heroic effort to account for backscattering. This had not been calculated before, but the results are really impressive. These are the results for the band curvature, which is accounted for in the charge mode, the red, and the solid lines are, again, the corrected data, corrected theory, and the dashed lines are just the raw data. And so you can see the advantage of correcting for the nonlinearities. It was really very strong. This dashed line moves up to the solid line, and then the agreement's very good. That's true here, here, here. The spin mode basically all had those discrepancies until we were able to correct for them with the backscattering. All right, so let me just mention before I finish up that there's also something called a spin incoherent Lettinger liquid. The spin and charge correlations are, of course, suppressed with increasing temperature, and that temperature is lower for the spin than it is for the charge because the spin becomes incoherent at a higher temperature. The spin mode is more fragile. So the energy scale for spin and charge are given here in comparison to temperature. This is a completely spin coherent regime, this is spin incoherent regime, and this is just thermal gas. So this is the data where primarily look at this plot. This is the speeds of the spin in blue and the charge in red. And you could see that once you get, as a function of temperature, you get to high enough temperature that there's a suppression of spin-charge separation, which is evident by the fact that they have the same speed at this value of temperature. And that's just about directly in the middle between the energy scale for the spin mode, E sub S, and the charge mode, E sub C. All right, so how much time do I have left? I have 5 minutes. Oh, okay, cool. Didn't realize that. So Majorana fermions are something that people have been chasing after for many years now, and there's really probably no definitive observation of Majorana fermions, but these are excitations that are also, like in the spin-charge separation, they are separated spatially at the end of the wires. This is a theory that was in a proposal done by Alexei Kitaev, and Kitaev suggested that since we don't have you need a P-wave interaction, and since we don't have P-wave superconductors, which think about that for a little bit, because we don't know why we don't have P-wave superconductors. We have P-wave superfluids in helium, but that's it. And so what he wanted to do is to use the proximity effect on a 3D superconductor shown in blue, and effectively then he showed that this was a P-wave superconductor, and the Majorana fermions might exist at the end of the wires. Unfortunately, P-wave Feshbach pairs or molecules are unstable, and they have a very short lifetime. This is, I think, 10 or 20 millisecond pulse, and at the end of that pulse, the P-wave molecules have vanished. They've they decayed to lower lying states. So we need to figure that out, and the field needs to figure that out. One open question, which is very important. All right, so, yeah, so this just describes how the atoms are lost. They form a molecule, and L2, diatomic L2, plus another lithium atom, plus some kinetic energy limits the lifetime to a few milliseconds. So at the moment, we've been trying, and so are these people, we've not been able to see a stable P-wave superfluid. This is just a list of some experiments that we're actively working on at Rice, and or results that we've made in the last few years. All right, well, let me acknowledge the people on this part of the lab. This is Ashish Kafli. This is Jimmy Ye. This is Ruin Senaratne and Daniel Cavazos. And the rest of the people are working on other experiments. And these are the theorists, Jiwen Yuan and Han Pu. All right, thank you very much.
Thank you, Randy. Do you have questions?
You were generous to me. I used 50 minutes.
On the Majorana furnace that you are describing, do we have really evidences already in any other experiment, or
I didn't
any
quite
evidences beside those type of experiments?
to get a P-wave superconductor.
Yeah.
Well, that's not answerable until we either make one or don't. I'm a little pessimistic at the moment. We spent a good 6 months trying various schemes to avoid the loss, and weren't able to succeed. But we'll keep trying.
Any further questions? No, I don't see. So thank you, Randy, again.
Thank you, Emmanuel.
Okay, we are good to go. We have our next speaker, Daniel Popmintchev. He will talk about quantum optics meets attosecond physics. Thank you.
Organizers for the kind invitation to present in Brazil. So this is my first time here, and I have some former collaborators in Brazil, and I hope to resume my work together with them. So today I'll talk about coherent X-ray upconversion, so based on high harmonic generation in a slightly unusual way, significantly different compared to what we do typically in our labs. And I'll focus mostly on upconversion where we have some pure quantum optics phenomena such as strong electron correlations and some record fast Rabi oscillations. So part of the work was done in my labs in San Diego, and before I forget, I would like to invite students from Brazil to apply to UCSD. So, and another part of the work was also done in the Technical University in Vienna, where we did mostly laser development as well as some X-ray upconversion. So for the students in the audience, I just want to mention that the coherent X-ray upconversion that we do is based on the extreme nonlinear process of high harmonic generation, which is, we like to think about this process as the fully coherent version of the Röntgen X-ray tube. So high harmonic generation happens when we focus intense femtosecond light onto a target, and this is a universal response of atoms, molecules, plasmas, and solids. So my focus today would be on high harmonic generation in gases, and typically in conventional high harmonic generation we have strong electric field, which in fact distorts the Coulomb potential. We create a finite barrier for the electron to tunnel ionize, and in most of the cases we limit ourselves to single tunnel ionization. So as you'll see in some of the regimes that I'll mention, we'll have more than one ionization events. And again, in conventional high harmonic generation, we have acceleration of, again, a single electron, and upon recombination, we have only one recombination event. Again, as you'll see in some of the regimes that I'll mention, so we have more than one recombination event simultaneously. So the excessive kinetic energy of the electron is emitted in the form of high energy photons. So these are our high harmonics, and our record today is combining more than 5,000 photons to create an X-ray photon of sub-1 nanometer wavelength. So again, conventional high harmonic generation, we produce harmonic bursts every half cycle of the laser field. This is due to the acceleration of the electrons within from the peak of the field all the way somewhere before the next peak. So whenever we want to observe effects which are related to multiple cycles, then, well, in general, so the next adjacent half cycle will produce also harmonic. So we need to make sure that phase matching, in fact, macroscopic phase matching, allows us to have a temporal window which is broad enough and to span more than half a cycle. So typically, again, in conventional high harmonic generation, we have a plateau with almost constant conversion efficiency. And the cutoff of the plateau is described by this simple equation where we have linear dependence on the laser intensity and quadratic dependence on the wavelength. So what's important for this talk is this factor of 3.2 at the front. So this is pretty much the cycle average kinetic energy of the electron, and we have some factor of 3.2, which gives us the maximum cutoff energy. So when we have linearly polarized driving field, the electron wave packet quantum mechanically oscillates along the polarization of the driving laser, and we produce linearly polarized UV or X-ray light. So here we have all these ripples of the electron wave packet. So the electron wave packet comes back to the fraction which is at the site of the ion here at the peak, and all these ripples are actually the source of our coherent emission. So, well, in fact, we can go beyond this one-dimensional case in terms of polarization of the driver, and I want to illustrate how we can manipulate the properties of the high harmonic light. For example, we can start talking about design of quantum properties of the high harmonics. Of course, you may think that we can shine a driving field with spin angular momentum or with circular polarization. However, the electron wave packet in this scenario picks up this beautiful spiral trajectory, so the wave packet never comes back and we don't have emission of harmonics. So of course, it's quite intuitive that we can put a second driving field with counter-rotating polarization. So they may have a similar frequency or substantially different frequency. But in fact, you can see over here in this animation that the electron wave packet returns in several predominant directions, and you have emission of X-rays. So the exciting thing about this regime is, in fact, the actual attosecond control of the electrons, which allows us to transfer, I'm not sure what happened, to transfer spin angular momentum from the drivers onto the generated X-rays. So I'm not sure if the cable. So I just wanted to illustrate what we can do nowadays in harmonic generation at the instant of the generation of the light itself. So we can generate bright light spanning from the EUV all the way to the X-ray regime. In some of the regimes, the coherent spectrum spans more than 12 octaves. So if we have a fine way to compress it, this will correspond to a pulse close to 2.5 attoseconds. At the same time, we may have this very narrow linewidth harmonics that are ideal for high-resolution imaging. So we have unprecedented spatial and temporal coherence. We have tunability from femtosecond to attosecond pulse durations. And in fact, some of our theoretical predictions talk about even sub-attosecond pulse durations. We can tune the spin and orbital angle momentum of the light, and so on. So my next question is, can we, in fact, take advantage of some quantum optics phenomena at the ultra-fast timescales, at the attosecond timescales, and how they are different from in this strong field regime? So, of course, our motivation in this research is to image matter at the space-time extreme. For example, if you want to access some of the fastest timescales, like motion of the electrons of atoms, molecules, and so on. So we can convince ourselves that in order to get to attosecond pulse durations, we need to have a flashlight in the Q electron volt region of the spectrum, or soft and hard X-rays. And luckily, high harmonic generation can provide both the short wavelengths as well as the short pulse durations. So just to give you an idea what we can do nowadays in the labs, in the extreme ultraviolet region of the spectrum, we can achieve near wavelength resolution when we image surfaces. The question is if we can extend this into the soft X-ray region of the spectrum. The question is if we can extend this also in the soft X-ray region of the spectrum with near wavelength resolution. We already have light there. Can we have the brightness as well? So some of the most challenging, most photon-hungry experiments can be done also in the extreme ultraviolet region of the spectrum. We can, in fact, now do magnetic coherent diffractive imaging or scattering from magnetic domains, not from electrons, and achieve a relatively good spatial resolution. So in the soft X-ray region of the spectrum, now on a tabletop, we can do various near-edge and extended-edge absorption spectroscopies. So we can also use light with spin and orbital angular momentum in the soft X-ray region of the spectrum and do some spectroscopic measurements. So recently we learned also how we can achieve full tunability of the harmonic peaks. And well, as you see, slowly we're starting moving the applications from the extreme ultraviolet region of the spectrum towards the soft X-ray region on a tabletop. And this is mainly due to our better understanding how we can phase match the process using ultraviolet drivers or mid-infrared drivers. Also, in some of the UV-driven regimes, we had to learn how we can manage dispersion, higher order dispersion. There is also convergence of laser technology, which is helping. Ytterbium lasers, for example, they're much more scalable in terms of average and peak power, and they allow us, in fact, to have the number of photons needed for the most challenging experiments here. Recently, we figured out using some new ytterbium materials how we can, in fact, get to pulse durations of sub-100 femtoseconds without any additional techniques. So this brings, in fact, ytterbium systems closer to the titanium sapphire systems from the past decade. So in the past, mostly we were focusing on X-rays generated by mid-infrared lasers. So they produce this phase-matched bright spectra, ideal for spectroscopic applications in the attosecond to femtosecond time scale. But my talk today will focus mostly on another regime where we have high harmonics driven by ultraviolet lasers. As you see, spectrally, they have narrow line widths, completely different compared to this supercontinuum that we have on the right-hand side. And in fact, this regime is broadly unexplored. So just for completeness, I want to mention that we can also do frequency and angular momentum mixing. We can achieve further tunability of the X-ray spectra. What you see over here is just a characteristic spectrum with left and right circular polarization harmonics. So again, we are able to extend this in the soft X-ray region of the spectrum. Well, a little bit on tunability in the temporal domain. So in fact, high harmonics can produce near transform limited at 100 attosecond pulses if we use ultraviolet drivers. Alternatively, if we use mid-infrared drivers, again, under phase matching conditions, we can generate really broad bandwidths at the zeptosecond frontier, where if we have find a smart way to compress the pulses, we may get to sub-attosecond pulses. So since I have been talking about high average and high peak power lasers, in some of the regimes we need to go towards a near clean room environment. And we are using, in fact, now a kilowatt class lasers, so both taking advantage of the high energy per pulse and high repetition rate. So we still use titanium sapphire lasers and, again, small-scale ytterbium lasers. So these are mostly commercial systems, but we did also some in-house development using new materials. And in most of the regimes, so we typically start with infrared lasers and we produce their harmonics. And we use their perturbative harmonics to drive the high harmonic up conversion. Alternatively, we can use also optical parametric amplifiers, again, to produce high order harmonics. Yes, and of course, all these experiments would be impossible without the strong electric fields that we need. And so thanks to the work of Gerard Morin and Donald Strickland, so our experiments are possible in the lab. And well, of course, the high harmonic work is also part of the quest for shorter and shorter time scales. After the invention of the laser, people started following picosecond chemical reactions, later on femtosecond chemical reactions, and last year Nobel Prize was on attosecond physics using extreme ultraviolet light and attosecond pulse durations to study motion of electrons. Some of the experiments, in fact, that we did were done on the optical table of Ferenc Krauss in the Technical University of Vienna. So this is a picture of the journalist that came on the day of the announcement of the Nobel Prize. So unfortunately, we already have replaced his vacuum chambers where he did the first isolated attosecond pulse measurements. We had already our X-ray beam lines and ytterbium laser systems. And well, I'll just finish this brief review on high harmonic generation with just mentioning that so the two regimes of mid-infrared driven harmonics and ultraviolet driven harmonics are well scalable towards shorter wavelengths. And in fact, if we use 6-9 micron driving lasers, we can access also potentially the hard X-ray region of the spectrum. So with potentially also sub-attosecond pulse durations. Alternatively, if we produce harmonics with ultraviolet lasers and multiply charged ions, we can access the short wavelength range as well before fully depleting all the electrons in the targets. And well, we're active in both of these regimes, but now I'll go a little bit beyond of these two regimes. So, and well, last thing that I want to mention is that we can produce also a single isolated harmonics, which we'll need, in fact, in some of the regimes that will be mentioning. So this is, for example, an isolated harmonic at the technologically relevant 13.5 nanometers, which is of interest not only for, in fact, high-resolution imaging of condensed matter samples, but also for the semiconductor industry, where we're talking about 2 nanometer nodes, and we want to image buried layers. So, well, now with this brief introduction, I would like to go now to the 2 new regimes of high harmonic upconversion. And I'll be focusing mostly on extending the emission into the X-ray region of the spectrum. So whenever we want to go to such extreme regimes, typically we would like to oversimplify the system. So I'll be talking about targets driven by a single laser wavelength in the ultraviolet wavelength range, or the driving laser will be also in the extreme ultraviolet region of the spectrum. So this is maybe some of the most extreme regimes that we have been working on in the labs. We'll also, when we talk about the soft X-ray region of the spectrum, my favorite atom is helium. So it's very hard to work with it, but in fact gives the brightest harmonics. And well, you may think that we have really low degrees of freedom in order to modify the properties of the harmonics. In fact, well, we can still scope the electron wave packet dynamics in helium. So we have 2 active electrons in helium, and well, there is also strong electron correlation between the electrons. So on top of this, so there is a question that we were asking ourselves, can we stabilize the electron wave packet dynamics? In other words, can we avoid the wave packet actually moving away from the parent ions such that this would not terminate the emission of high harmonics? So in other words, can we avoid strong ionization? And well, this kind of leads me to maybe the ultimate regime of upconversion, maybe my wish list for coherent X-ray generation in the lab. Can we have a regime where we can have fully phase-matched X-ray upconversion, nearly fully group velocity matched upconversion, and can we also minimize the ionization-induced depletion of the ground state? So I'll start with the first regime where we have electron correlations and we use ultraviolet lasers at 400 nanometers. The second regime that I'll cover in a little bit later will use 60 nanometer light, and again we extend the emission into the soft X-ray region of the spectrum with some attosecond Rabi oscillations. So why do we care about ultraviolet lasers? So in fact, when we move from the infrared region of the spectrum towards the ultraviolet region of the spectrum, they are both favorable macroscopic and microscopic effects. So in terms of phase matching, so the neutral indices of refraction of neutral atoms and ions increase as we approach resonances. So these laser wavelengths also experience less the plasma dispersion. This means that we can in fact operate at much higher laser intensities without destroying phase matching. So then if we move from the near-infrared laser wavelengths to, let's say, their second harmonics, we can, due to reduced quantum diffusion of the electron wave packets, we can have boost also of the emission per atom. So the factor here is on the scale of 2 orders of magnitude. If we combine macroscopic physics, the boost is again kind of close to 2 orders of magnitude enhancement in the brightness. So this, what I showed on the previous slide is actually shown as a cartoon. Here is shown as an actual calculation where if we use helium, we can have a strong increase of the brightness of the harmonics moving towards UV drivers. So one last component that I want to list over here is the temporal domain. So when we use ultraviolet lasers, in fact, without going into details, I just want to mention that we have, in the time domain, we have effective phase matching window, which is relatively broad. In other words, we have contribution of harmonic bursts through a large number of half cycles of the driving laser. So this is due to the fact that indices of refraction of ions are also helping us. This is not the case when we use infrared lasers. The temporal phase matching window is relatively narrow. So in other words, if we want to observe a phenomenon related to multiple cycles, so in other words, thermal ionization of electrons over in adjacent cycles, we would prefer to use the ultraviolet driven regime. So here, this brings me to the first experiment. So we put a substantial effort to oversimplify the interaction geometry as well as detection geometry with the goal to observe lower probability events. So here we've coupled it in a waveguide 400 nanometer light, and well, we use also conical diffraction gratings in order to improve the efficiency of the detection. So we use multi-cycle driving pulses in order to observe multi-cycle effects, and I will skip these details. We optimize dispersion in the systems as well as our spectrometers. What I want to mention simply is just we started using different geometry of detecting of the X-rays, where in fact the lines of the gratings are nearly parallel to the K vectors of the incoming X-rays. So in this particular geometry, you can have diffraction of the X-ray wavelengths along an arc of a circle over here. So the interesting thing about this regime is that the efficiency of the spectrometer is relatively large. Typically, a high harmonic spectrometer may have an efficiency of 1 to 10%. Here in some cases, we'll have efficiency of close to 85%. And well, S&P polarization allows us also to, in fact, preserve the circular polarization of the X-rays in some regimes. So, in fact, in this regime, what we learn is how we can eliminate aberrations of the beams and use this geometry also as a imaging geometry, like a tunable X-ray mirror. And here is an X-ray spectrum driven by ultraviolet laser focused into a helium medium. So what you see over here on this arc is the conventional X-ray plateau from helium and neutral helium and helium ion. And then, well, surprisingly, over here we have a large extension beyond the conventional cutoff that goes all the way to the soft X-ray region of the spectrum. So this secondary plateau is actually 4 orders of magnitude weaker compared to the first one. And it does not obey the usual cutoff rule. In fact, if I take a line out of the harmonics, so within the conventional cutoff, we can see these bright harmonics, which are ideal, for example, for metrology for the semiconductor industry. However, beyond this cutoff, we have weak signal, which I would not use as a source, but rather due to the underlying physics, we can use this signal as an indicator for highly correlated electrons. So initially, we were in fact, so this extension of the cutoff is more than 150 electron volts. Initially, we were looking for electron correlation effects where probably we're expecting 20 to 30 electron volts extension of the cutoff. And our original idea was the following. So we knew that instead of using infrared lasers, if we use UV lasers, we can enhance the following probability. So in helium, we can in fact excite one of the electrons to a Rydberg state, while the second one can go down to a strongly bound state. So having effective higher ionization potential in high harmonic generation, this simply translates into extending the high harmonic cutoff. So if you look at this TDSE calculations with 2 active electrons, you can see that the emission from helium and helium plus stops at about here, and the rest of the emission is due to the correlation between the electrons. So we can do the usual time frequency analysis, where in the vertical scale here we have the photon energies, and we can convince ourselves that this kind of extension of the cutoff is due to electrons talking to each other. However, in the experiment, we observe much higher extension of the cutoff. So in fact, the cutoff obeys slightly different rule. So we have a factor of about 5.5 in front of the cycle average kinetic energy of the electrons. And well, this scaling, of course, involves also the ionization potentials of the 2 atoms. And in fact, while doing this experimental research, we found some papers from the 90s where they were, in fact, studying some similar physics. So to illustrate the underlying physics, I'll go back to the simple man's 3-step model, where in conventional high harmonic generation, if I use ultraviolet laser, I have tunnel ionization of an electron, which is accelerated away from the atom, and upon recombination, I have this maximum cutoff, which scales as 3.2 times the cycle average kinetic energy of the electron. So in our regime, what we have is, in fact, using UV lasers, we increase the probability of the following phenomena. So we may have two ionizations of two electrons and simultaneous recombination in space-time of the two electrons. So this double electron recombination, in fact, effectively brings two kinetic energies of the electron to the cutoff rule, where, in fact, in this particular case, we may have a factor of 4.7. So this is the case where the two ionization events were in two adjacent half cycles. So this temporal separation, in fact, is needed because if we have non-sequential double ionization, in fact, the probability of the two electrons to recombine is really small due to the longer time of Coulomb repulsion during the boomerang trajectories. So there is a second scenario, which is also with finite probability, where the two ionizations can happen within approximately full cycle of the laser field. Then upon simultaneous recombination, now we have slightly larger kinetic energy for one of the electrons, and then the cutoff is extended a little bit further. So whenever we have such rescattering physics or such boomerang trajectories, we would like always to convince ourselves that we have coherent emission, and it's due to the rescattering physics. So typically what we do is we, instead of using driving lasers with linear polarization, we change the ellipticity towards circular, and high harmonic emission should terminate. So on the vertical scale over here, you have you can think that this is the ellipticity of the driving field. So within the conventional cutoff, the harmonics disappear as expected, and in fact, the secondary plateau that I'm illustrating over here has even stronger dependence on the ellipticity of the driver. Of course, we have longer trajectories over here, and it's kind of expected this to be with a larger sensitivity to ellipticity. So this is the case from helium. Again, just to mention, so helium and helium plus, they emit harmonics up to this first cutoff. The secondary emission is due to electron-electron correlations. And in fact, if we use any other gases, argon, neon, with a larger number of outermost electrons, you can see that there is no signature on this log scale of secondary plateau. So this is our characteristic signal of electron-electron correlations. So again, as I mentioned, we can solve fully the TDSC equation in one dimension with two active electrons, and we can convince ourselves that this higher secondary plateau is due to electrons talking to each other. So I'll summarize this regime with Feynman diagrams. So we know that they are not built for AMO physics, rather for high energy physics, but this helps us a little bit maybe to follow the process, because as you see, we are going to a little bit beyond three-step model. So in conventional high harmonic generation, we start with electrons in ground state. We absorb some, let's say, odd number of photons. The electron ionizes, and we go to Volkov states or continuum states. And upon recombination, the electron goes to ground state, and we emit a high harmonic photon. In our process, we have two correlated electrons in helium. So the ionization of the first one, in fact, excites the second electron to an excited state. And now, in fact, otherwise the laser intensity will be not enough to introduce any dynamics to this second electron. So here, with some time delay, we have another ionization, or going to Volkov state. And upon recombination, simultaneous recombination of these two electrons, we emit an X-ray photon with higher cutoff energy. So what I want to mention for the experts in the audience is, in fact, that these generated harmonics are also odd harmonics. So this means that kind of if we talk about absorption of photons over here, we need to think of odd and even number of absorption of photons by each of the electrons. And if the time delay between the two ionization events is slightly longer, then in fact the energy of the produced harmonics is with slightly larger cutoff. So, well, this kind of spectroscopic observation kind of suggests that we may start doing attosecond electron correlation spectroscopy in atoms and molecules. So far, we are working with helium and hydrogen with two active electrons. And we are trying to find a way how we can produce hydrogen -1 in the lab, which to my knowledge is the system with the largest correlation between electrons. And we are looking also into extending and finding some similar physics in high harmonic generation from solids. So with this said, I'll switch gears towards the second regime. So this regime is in fact involving extreme ultraviolet drivers. And the question is, can we produce the X-rays? In other words, can we use high harmonics to generate high harmonics? And this is maybe the most extreme regime that we have analyzed in labs. So we're talking about EUV intensities that we want to reach of 10 to the 14, 10 to the 16 watts per square centimeter. And in some of the high harmonic regimes, we estimate that we can do this. So for the experts, so this means that we will be above the barrier suppression regime for helium, which is at close to 10 to the 15 watts per square centimeter. And in other words, we'll have a barrier which is suppressed such that the electron wave packet can almost freely leak out of the helium target. So we'll be driving this up conversion at a resonance. And well, the driving photon energy will be very close to the ionization potential of helium. And again, for the experts, so we'll be operating at Keldysh parameters of 2 to 20, which means that we're in the so-called single to few photon ionization regime. So in this particular picture, if you look at the photoelectrons in momentum space, typically in such a multi-photon ionization regime, we may expect the electrons to have symmetrical distribution in space. So this is slightly different to the most of the regimes that we work in the lab right now. So this regime is beyond the three-step model in high harmonic generation. And as I will illustrate in a little bit, we identified some really fast Rabi oscillations in this resonance conversion. So typically in the rest of the regimes, the electron wave packets are mostly aligned with the polarization of the laser. And so over here in our regime, so most likely we expect more homogeneous distribution. So the first question is how we produce bright harmonics to do nonlinear optics over here. So we do know that if we use ultraviolet lasers, we can produce isolated harmonics, which have record high conversion efficiency of 10 to the -4 or so. And the next question is, can we have the tunability to have resonance experiments? We have also the high peak power and average power laser systems for these experiments in the lab. And of course, we can do these experiments at XFEOs as well. So we have also some laser development of high energy laser systems at lower repetition rates as a risk reduction. And as I mentioned also, we have already with the terbium sub-100 femtoseconds. Typically, terbium lasers gives you 200, 300 femtoseconds. New materials allow actually these systems to scale even further. So to achieve tunability of the driving laser, here we start with titanium sapphire or a terbium laser system. We go through a hollow waveguide and we fill it either with atomic gas or molecular gas. So the atomic gas gives us SPM, cell-phase modulation, where we can mostly use the blue shift of the laser light, while the molecular gases, they give us asymmetric stimulated Raman scattering, which in fact is extending the light more towards the infrared region of the spectrum. So with such a scheme, we can have second harmonic of, let's say, of ytterbium, which is tunable between 470 nanometers to 580 nanometers. This gives us already full tunability of this visible driver. Now, this is translated in also an extreme tunability of the high harmonics. Typically, high harmonics from UV drivers, they have large separation in energy between the harmonic peaks, so it's hard to tune them. However, with the project I mentioned, we can have full tunability in the blue direction of the harmonics as well as in the red direction of the harmonics. So now I'm coming to the actual idea. So we would like to hit 1s to 2p resonance in helium atom. So this corresponds to approximately 18.4 electron volts, or our driving laser needs to be at approximately 67 nanometers. So here is the population of the ground state and the excited state versus time, and as a function also of the driving laser frequency. As you see here at resonance, we start at fully populated ground state, and within a couple of femtoseconds, all the population now is in excited state, and this follows Rabi oscillations on the scale of a femtosecond or so. If we look at the emitted light, you'll see that we can generate third, fifth, seventh, ninth harmonic. So they have some spectral structure. So for the experts, the spectral structure is not due to interference of short or long trajectories, but rather due to the Rabi oscillations. So now with harmonic order of 9, we're already in the soft X-ray region of the spectrum. So kind of with very low harmonic orders, we can move from the EUV into the soft X-ray region of the spectrum. So, of course, we can probe this regime in a slightly different way. So, we can drive these Rabi oscillations with slightly larger amplitude. So there is and we can create faster Rabi oscillation at sub-femtosecond timescales. Here is an example of 800 attosecond period. So within the change of the amplitude of the driving lasers within an order of magnitude, in fact, we have extremely bright upconversion over here, which changes close to 7 orders of magnitude increase in brightness. So it's interesting to look what happens with the population in the ground state. If we start with fully populated ground state, in fact, at such laser intensities, typically for other regimes of resonance, within few laser cycles, we are already fully depleting the ground state, such that we stop producing harmonics. However, due to these Rabi oscillations, we do have not fully repopulating the ground state. There is some kind of depletion of the electron, so slightly leakage of the electron wave packet, but still, within multiple laser cycles of 20 to 30 laser cycles, we still have substantial population at the ground state, which keeps producing high harmonics. So this adds up to the efficiency of the upconversion process. Thank you. So, the question is, can we identify these rapid Rabi oscillations spectroscopically if we do not find initially a technique to access the time domain? In fact, if we look at the third, fifth, seventh harmonic, we see this at resonance. We can see this double peak structure of the harmonics. This is expected for a two-level system. Here is on a linear scale, the third harmonic. So you see the two side peaks at plus minus Rabi frequency. So the next question is, this is the emission from a single atom. What happens if we include any propagation? So we can include a Gaussian profile and short propagation, and you can see that in fact there is a robust picture where instead of 2 peaks we have 3 peaks. So we are moving slightly off resonance, so this is likely the reason why there is the appearance of a third peak between the two side peaks. And with this said, I would like to conclude on this regime. So I did not talk about phase matching, but since the driving laser frequency and the generated frequencies are very close to each other, and they are in the UV and soft X-ray region of the spectrum, we have nearly automatic phase-matched upconversion, also almost perfect group velocity matching, and something that was unexpected to us. So at this, with this attosecond Rabi oscillations, we may expect really low ionization depletion of the ground state, such that we can produce harmonics over multiple cycles. So I will skip our diagrams, and with this I want to thank sponsors as well as collaborators. So most of the theoretical work was done by the group of Luis Plaja and Carlos Garcia at Salamanca. So lots of the, most of the laser development and X-ray generation was done in Vienna in collaboration with Andreas Boltuška, and these are some of the postdocs that work on these experiments, as well as my PhD students at San Diego. Thank you very much for the attention.
Thank you. Questions, yes.
Thank you for the very interesting talk. I'm not from the field, so it may be a stupid question, but I was wondering if you described this two-electron recombination. Is it something that can happen at a higher order because you use multiple electron atoms? So can we imagine that this also happens with 3 electrons, for example?
Electrons, 3-electron recombinations, likely this is a very low probability process. So when we look in the literature back in the 90s where people were doing just simply theoretical calculations with 2 active electrons, they figure out that the difference in intensity between the 2 plateaus is 10 to the minus 10, something that experimentally we were not able to observe. So, however, they were using mid-infrared lasers. In order to improve our probability, we knew ahead of time that we need to go to ultraviolet lasers. The electron wave packets, they do not expand as much, so we increase the probabilities of such lower probability processes. So I would expect I'm not sure if anyone has looked into this, but I would expect the probability to be really low and most likely unobservable.
I want to understand the source of the second electron. Is this direct tunneling from the bound state, or is there some Rydberg trapping or shake-up or anything like that?
Shake-up.
You think it's shake-up that's happening?
Yes, we think it's shake-up. Okay. Usually with TDSC, you know, it's a little bit harder to extract the physics, but luckily you have most of the physics in. So there are also already models in Vienna that can do 2 active electrons in 3D. Our simulations are in 1D. In other words, you can think about the 2 electrons are positioned along the polarization of the driver. But there is always models that we can study this in 3D.
Okay, then I'm going to cheat because you answered that one so quickly. What is the technology barrier so that everyone can have attoseconds? What is the primary technological barrier, do you think? Is it the laser? Is it the high sapphire? What is it? Or the yield of HHG?
So I think these are a little bit more expensive experiments because of the ultra-fast lasers, the vacuum systems that are involved, and X-ray optics. So ytterbium systems being much more turnkey compared to high-end titanium sapphire systems, I think already we may have more accessible attosecond science. So ytterbium systems, the semiconductor industry, in fact, pushed the prices of the vacuum system substantially now with the CHIP Act. So I think this is still
very nice presentation. So I was wondering, in your second plateau, it seems that you don't see the harmonic structure. And you know, from the point of view of if you have coherent radiation and you do the Fourier transform from your multi-cycle emission, you should have something similar, right? But it's very clear that on one side you have harmonic structure, on the other side you don't. Could you comment on that?
So in terms of coherent and incoherent emission, so due to the fact that with circular polarization this disappears quite fast, I'm kind of quite confident that this is coherent emission. So of course this is signal which is 4 orders of magnitude weaker, so meaning that we need to do longer exposures. So this is simply a technical difficulty, not that this. So the reason why we would like to see the harmonics there is probably I briefly mentioned about it. Numerically, we see that they need to be odd harmonics, and kind of initially we were thinking that probably since we have 2 active electrons, right there, each of them are, you can think semi-classically, they're absorbing some photons from the fundamental. So why do we need to absorb even an odd number of photons from each of the photons, right? So in other words, we do know that these are odd harmonics numerically, but we have not confirmed this experimentally, yes. So this is simply exposure. With such laser filters and such average power, we cannot have long exposures. Yeah. This is the challenge.
Okay. Thank you very much. And with this, we end this session.
Yes, thank you.
Just a quick announcement, which is really an invitation For those of you interested in getting to know our labs here, we are organizing a lab tour 1 hour from now, so you have some time to get lunch. And then at 1:45, we meet in front of the building. You have the opportunity to get to know our Bose-Einstein condensates, both of them, and the third one under construction, and also one experiment with strontium, which is cold but not condensed, that they study light-matter interactions. And an atomic clock.